Hello, I am Joe Bakos, and I'd like to welcome you to this week's edition of the Torus Report. We are doing a little digression this week to learn about rotation in quaterns. Quaterns are a new measure of angle rotation, and so what's the big deal? Why bother with a new measure of rotation? Well, traditional measure, degrees and radians, and all of the trigonometric functions that are associated with them are what we call transcendental. That means to find them, we've got to do infinite sums. And so they are not algebraic. Rotation in quaterns allows you to do all of those trigonometric functions algebraically. So if you're doing like sine or cosine, or the inverse trig functions, or if you're doing rotation of vectors in space, cross product, dot product, all of those things using quaterns become algebraic. And so there's the potential here for, like with computer graphics and programming, there is the potential to cut down computation time by quite a bit, because right now technology has to do truncated infinite sums to do these functions. And with quaterns, that won't be necessary. The only truncation would just be rounding. So I would like to just demonstrate the use of quaterns, and part of this is a proof that they actually work, because oftentimes when I tell people that there's an algebraic way to approach rotation, they don't believe me. So I want to demonstrate that it actually works by solving a triangle using purely a quatern measure. Before we get started, there's a few things that I would like to mention. First, the Torus Report, after today's digression, will go back to speaking about cosmology. Just doing this little digression this week because I will soon be publishing a paper on quaterns. And that brings me to the other point I would like to mention, is that all of the calculations, I have set up a graphing calculator site using Desmos so that anyone can do all of the calculations that I'm about to demonstrate. You can do them quickly and easily because I will be putting links to all of the sites, all of the calculation sites that I'm using. I'll put links to that in the comments of this video, and also a link to the paper that will soon be published on this. So I will have a link to this paper, Solving Triangles Algebraically. And so you will be able to try it for yourself. Try the calculations yourself and see how to work with quaterns. So with that said, let us get started on solving this triangle. So first, what is a quatern? First, what is a quatern and how do you calculate it? So in the first quadrant, it's very simple. And we use the Greek letter kappa. It looks sort of like a lightning bolt or a backwards N sometimes to represent the angle in quaterns. And in the first quadrant, it's very simple. It is y coordinate minus x coordinate divided by the radius plus 1. And so that is the angle in quaterns. Now it so happens that if you go all the way around the circle, that equals exactly 8 quaterns. So, for example, let us suppose I've got some point here. Okay. And let's suppose I've got the point let's suppose we're using the point 4, comma 3. Okay. Now, I picked that one because I happen to know what r is. So if you don't know what r is, you can always get r, which is the distance from your point. So if I graph this point, well, let's see, I didn't draw that very well. Let's try and put the axis like right on the line. Let's try that again. So there we go. Let's try that. So here's my axis. This is the first quadrant. The formula is, so that is what kappa equals, and I have picked the point 4, comma 3, just because I know if I graph that point, like say I graph it here, here's the point 4, comma 3, I happen to know that the hypotenuse, which is the distance from the point to the origin, I know that that's 5. Okay, and if you don't know what the hypotenuse is, you can always calculate it by doing this. Square root of your x-coordinate squared plus your y-coordinate squared. You add those together and take the square root, and that is going to be the distance to your point. So this measure here, as far as quaterns, would be simply y-coordinate, which is 3, minus the x-coordinate, which is 4, over the distance to the origin, or r, which is 5. So 3 minus 4 is -1. So we have -1/5 for this fraction, plus 1. Now I will rewrite 1 as 5/5. So I'll do 5/5 minus 1/5 equals a positive 4/5. And so this angle, in quaterns, the angle would be 4/5. So that is the basic idea of how you calculate it. Now, in the first quadrant, it's super easy because the formula is very simple. Now, it gets more complicated if you try and do it in other quadrants. Then we have a much more complicated looking formula that is actually more complicated than it is actually less complicated than it looks. So if we go down here, so this is the formula for quaterns that is valid in all 4 quadrants. Okay, now the formula looks intimidating, but it's really not, because whenever you see this like y over the absolute value of y, it just means y-coordinate over the y-coordinate, make it positive. Absolute value just means make it positive. And so these quantities here, like y over absolute value of y, or x over absolute value of x, all of those are going to be either 1 or -1, right? They'll be 1 or -1. And so when you do this calculation, like in the other quadrants, it's actually quite simple, and it's not difficult to do at all. So the point is, there is an algebraic relationship always between the coordinates of a point and the angle in quaterns to get to that point. So if you had a something, extreme, like let's say in quadrant 4, right? So let's say you had a point like here. Right, so this one is what, 4 comma -4, right? Now to get to that point, you'd have to rotate. So first I draw a line straight to it. You'd have to rotate all the way around like that, right? Now if you go all the way around the circle, like I said, that's 8 quaterns, so I'm assuming this is going to be like 7, something like that. Actually, I kind of know it's 7 because 1 quatern is approximately equal to 45 degrees. Okay, so 1 quatern is exactly 45 degrees. So that's just the basics of how you would calculate the angle in quaterns, and then we will go on from there. To solve a triangle, we need things like the trig functions, sine and cosine, and we need the inverse trig functions like arcsine, arctangent. And quaterns have all of those things in another form. We'll call it the analog form of sine and the analog form of cosine. And as I said, calculating sine and cosine in terms of quaterns is algebraic. It is not a transcendental function. So traditional trig functions and inverse trig functions, they have to be done as sort of truncated infinite sums, and that is not the case with quaterns. You have exact algebraic expressions for sine and cosine. Now, I have calculators, online calculators, and as I said, I will be sharing the links for those. But it's enough that you can see that these formulas, if we're solving a triangle, we're only going to be talking about quadrants 1 or 2, okay? Because all of our angles are going to be between 0 and 180 degrees. So figuring the quatern angle in quadrant 1 is this. I've already explained that. This big equation here for quadrant 2, as I said, it simplifies nicely. In quadrant 2, it simply becomes that. So very easy. Then the trig functions for quadrants 1 or 2. Now, quatern trig functions and inverse trig functions are completely valid in all 4 quadrants. I'm only including quadrants 1 and 2, acute and obtuse angles, simply because I'm presenting this in the context of solving a triangle. So we don't need quadrants 3 and 4 for that, but I need everybody to know that we have those equations for the other quadrants. It's just that for solving a triangle, we don't need them. And all of these, as I said, I will put a link to this paper and I will put a link to all of the calculators so that you don't have to actually do all these formulas by hand, like plug it all in and calculate, because I have that all set up for you already with the online calculator. So with that said, let us get to the triangle we want to solve. And it turns out that with the analog trig functions and inverse trig functions, you, in essence, solve the triangle the same way you do with traditional measure, except that it's all algebraic. The functions are all algebraic. They are not transcendental functions. So let's jump to it and get to solving the triangle. So the first one we want to take a look at here is this triangle, and it's an example of an ambiguous case, right? So this triangle is an angle side-side, it's called, and it presents an ambiguous case because there's 2 different possible solutions. They give you this angle A here. They give you this side C here, this large side right here, and they give you this the side opposite A, which is side A, over here. Now, what you don't know is you don't know angle B, and you have 2 options for angle B because this is an ambiguous case, and you don't know angle C, and you've got 2 options for that as well. And so we will work on solving this triangle. The first thing we're going to do is the only transcendental part of all this. When you go from degrees to quaterns, or you go from radians to quaterns, that aspect is actually transcendental, and you have to use infinite sums to go back and forth. However, I want to emphasize that if you have, like, let's say we located this triangle, on like if I was to give you coordinates for the ray that is forming side A, then all calculations could stay completely in quaterns, and you'd be able to totally solve the triangle. Like if I gave you the original angle in quaterns, then you'd be able to solve the triangle completely without doing anything transcendental. So the only transcendental aspect of all of this is going to be just figuring what is the exact quatern measure of angle A. And we can do that with this sum, which is at this website here, from theta to kappa. As I said, I am going to link this paper, and I am also going to link all of these calculator websites. So notice that angle A is 42.9 degrees. So I go to this website here, and I'm going from theta to kappa. And K I set depending on how accurate I want to be. I don't want to make it too high because then it takes a lot of calculations. But I'll set it at 1,000. That'll be sufficient for us. And so if I set it at 1,000 and then I enter my degrees here of 42.9, I already have it in here from doing this before. But let's say I enter in my degrees 42.9. Then down here is the quatern measure of that angle, and I will write this down. The quatern measure is 0.948. Let's go to 4 significant digits, so I'm going to write this down as 0.9482. Now, while I'm at it, I am going to go to another calculator site I have here, wherein you can put in the quatern measure, and y sub a, that is the sine output for any angle in the first quadrant. And we know that this quatern angle is in the first quadrant because it is less than 2. Quadrant 1, in terms of quaterns, are from 1 to 2. Okay, so we're in the first quadrant. So here we could just enter in the value that we just found, which was 0.9482. And then it will output for me what the sine ratio is for that. Okay, so y of angle A, and I call the sine ratio for angle A ya, and that equals 0.6807. And that is how I round it. So this is what we have so far on our paper here. From the calculator, we translated from degrees to quaterns, and now that we're in quaterns, we don't have to go back to degrees until all the way at the end. The rest of the triangle can all be solved in quaterns, and then we can translate back into degrees at the very end. So this is the quatern measure of angle A, and this is the sine ratio, the quatern sine ratio of angle A. So the next thing that we want to do then is we are going to try to set up an equation just like we would solving a triangle in trigonometry. Those of you who have had trigonometry or pre-calculus, it is solved in exactly the same way using the law of sines. And so notice here, this is if we had wanted to do that calculation of the sine ratio by hand, right? We could have done that because that calculation is algebraic and the formulas were presented earlier in the paper. So everything that I just did with the calculator online was for convenience, but it could have been done algebraically using this formula to get this sine ratio. Okay, and so then the next thing we want to do is use the law of sines, where we find that we want to solve for the sine ratio of angle C. So let's take a look at that next. Traditionally, using the law of sines, the way you would set this up is you would say that side C, right, is proportional to the sine of C. So you'd set it up like this. Sine of angle C over side C is proportional to sine of angle A over side A. then you would multiply both sides of this fraction by side C, and you would get this. Sine ratio of side C, or I'm sorry, angle C, is going to be equal to side C times the sine ratio of angle A over side A. And we do this exact same thing in quaterns using the analog sine function in quaterns. And so we can find out what this sine ratio is by doing this calculation. Notice we already found sine of A to be this, right? And we know what side C is. And so this becomes 12.86 times 0.68 over side A, which is 8.98. Okay, so if we do this calculation, then we will know what the sine ratio for C is. And this calculation has already been done here. Okay, and so we find that the sine ratio for C is 0.9748. 0.9748. Now, notice that for the sine ratio for C, since that number is less than 2, that means that is an acute angle. And remember, we have two options for C, right? We have two options for C here. We have an obtuse angle, and we have an acute angle. So since we got a value for C in this case, that is acute because it is less than 2, then that means it's this one. So this is y of C, which is the sine ratio for C. Whoops, I wasn't showing you the video, so let me show you this. So anyways, as I was saying, since we have two options for C, this one is obtuse, and that means that this angle in terms of quatern is going to be greater than 2. This one is acute, which means that in terms of quaterns, this angle is going to be less than 2. And we found that the sine ratio for this angle, because it's less than 2, we know that we just found the acute solution, and that sine ratio is 0.9748. Now, once again, we can go to, we have a few options. Now, you can calculate the inverse trig function using the formulas that I have up here, right? These are the arc sine and arc cosine. So for acute angles, we would be using this formula. And so if we plug that sine ratio in here and here, and calculate, we will get the output of what the quatern measure of that angle is. Now, since we have the online calculator, we will use that. And I have the inverse trig functions down here below. Okay, so if I go down here, I can find the inverse trig for y. So we want inverse sine function for acute angles, and I can plug in the value that I just found, right, by calculating, and that value was 0.9748. And then the output will be the measure of the angle in quaterns. And so I find that this option for C is 1.752. That is the quatern measure of C. And so we have found the sine ratio for this option of C, and we have also found the measure of the angle in quaterns for C. So now we have two angles of our triangle in quaterns. We have this C option, and we have A. So these are the measures of our two angles. Now, if we had two angles in ordinary measure, like let's say degrees, then we know that all the angles of a triangle must add up to 180. Now, in quaterns, they must add up to 4. But the problem is that adding and subtracting angles in quaterns is only direct if you're willing to do approximate. Like, in other words, if I just add these two numbers together, right, and then subtract it from 4, then I would get this angle, because we've chosen this C, it means the angle for B that we're talking about is this larger one, right? Later, when we find this option, then the angle for B would be this smaller one. But since we're talking about this option, it's this larger one. But in any case, common sense would say that very roughly, 4 minus this one, right, should give us angle B. And for quaterns, that is only roughly correct. So if you're doing approximations, that would be okay. Now, if you want an exact answer, though, you have to use the Quatern analog angle addition formula, which I have in the paper. And again, I have a calculator for that as well, adding two angles. And so I am going to go and add these two angles, and it will conform to this formula, which is in the paper, which is the angle addition formula. But I can do it at this site where it is entitled, and I will link this, where you just enter angle 1, you enter angle 2, and it uses that algebraic formula. So again, none of this is transcendental, right? It's all algebraic. So I'm going to go ahead and put the first angle in there, which was 0.9482. That was my angle A. And I'll put the second angle in there, which was 1.752. That was angle B. And then the sum of those, using quatern angle addition, the sum of those is this value down here, 2.63, let's call it 5. So 2.635. 2.63, yeah, rounding up, 2.635. So this is my angle B. Well, no, I'm sorry, I'm being a little hasty. This is adding angle A and angle C together. It equals this. So coming back to my paper, so I found out using the rules of quatern addition, I found out that adding these two together gives me this. This is not angle B, but angle B must be 4 minus this. And when I subtract those two, then I have this option for angle B. And so subtracting those two, this option for angle B must be 1.365. Once we have that, it is always helpful to use the online calculator or else to use the formula. Like once you know what the angle is, it's always helpful to go ahead and find the sine ratio, because chances are we're going to have to use it. So we can go to the online calculator or use the formula in the paper to do that. So let's see, we want to go to here, and we want to do the sine ratio, and since B is acute, 1.365, that is less than 2. So if it's less than 2, it's acute. So I'm going to be using this one rather than the obtuse option. So 1.365. And that tells me Oh, this is the obtuse one. This was the inverse. I'm sorry, that was the inverse. I have to scroll up here. This is where I meant to enter it, right here. So I just entered it into the inverse. So let's try that again. So 1.365, and this tells me that the sine ratio for this angle is 0.86, well, let's call it 0.8656. .8656, we'll call it. That is the sine ratio. Now, the only thing left to solve in our triangle, since now we know all three angles and we have two sides, the only thing left to solve is this side opposite right here. And we use a similar law of sines setup. So in order to find side B is going to be equal to, and I'm going to compare it to the proportion of A and sine of A, since that's what was given in the problem. So side B is going to be equal to A times the sine of B, right, over sine of A. Now, we already have these two sine values. There is the sine of B right here, and sine of A we found earlier, and side A, of course, is this. And so we can just put those values in the calculator. If we just take side A is 8.98 times the sine of B, which is 0.8656, divided by the sine of A, which is 0.6807. I almost entered the angle instead of the sine ratio. Right? So these are the sine ratios, not the angles. So let's make sure that we entered the right thing. Sine ratio of B and sine ratio of A. So then that tells us that this long length here, because we've done this acute option, this long length here is 11.42 units. Now let's look at this obtuse option here. Now notice we got the sine ratio for C early on, and the truth is that this sine ratio is the same whether we are talking about the acute option or we're talking about the obtuse option. Now the only difference in our output is I put this as an input into the acute inverse sine. Now if I take this same value, 0.9748, that sine ratio, and I do the inverse sine option for obtuse, which is a little bit different. So in other words, if I go down here and I find inverse sine option, right, let's see, there's x acute, here we are. So this is the inverse sine option for obtuse angles. And if I put that same exact value in here, last time I put it in the acute option. So if I put 0.9748, I get a different output for angle C. So notice here that now my angle, and again, all of this can be done algebraically. I provide the formulas in the paper. So none of this is transcendental. So I get a sine ratio for C of, and let me write this down here. So we've got y of C obtuse is, or actually no, this is the actual angle. the sine ratio is the same as the acute one, but the angle is different. So the angle is 2.2, let's say 48. Yeah, let's call it 2.248. So that is our angle C. And then that will give us a different value. So now that we did that, so now we've got a new value for C. Then we want to go to our angle addition again. Because remember, we did A and C last time to find out what their sum was. So now we have to do A, angle A, and the new value for C, which is 2.248. That is our new value. And we find that that sum is here. And that sum is, and I'm just going to write this down real quick. The sum is 3.264, let's call it. 3.264. So that is the sum. Now, since that is the sum, since this is the new sum, all we have to do is 4 minus that, and then we'll know what our new angle B is. So 4 minus 3.264. So we have a new angle B of 0.736. So this angle B here is 0.736. And then, as before, I'm going to go ahead and find the sine ratio of that, just because we're going to need it anyway. So if I go to my triangles again, and that is an acute angle, so I can enter it in here, 0.736, and I get a new sine ratio for B of 0.5627, rounded. And then once we have that, then we can go back and redo this calculation again, right, in order to find this side B. And we can see from the diagram that this version of side B over here at the bottom should be significantly less than 11.42. We use the same exact equation, and the only difference is that now we have a different sine ratio for B, right? Everything else is the same, but we have a different sine ratio for B. It's this new value right here, whereas before it was that value. So if we do this new calculation, side A is 8.98, and we're going to multiply by our new sine ratio for B, which is 0.5627, and then we'll divide. So doing this calculation again, right, we're doing this formula with our new sine ratio for B, which is this. So we have side A times that sine ratio divided by the sine ratio for A. So we've got side A, 8.98, times the sine ratio for B, 0.5627, divided by the sine ratio for A, 0.6807. And so we find that this side has become 7.42. Now, one can solve all this usually using a traditional angle measure. But I would like to just speak a little bit about what all this means. So note once again that all of these calculations have not been transcendental, and at the end I did not do it, but you could use the calculators that I will supply to go back into degrees. We found the quatern measure of all the angles of that triangle, and we also found all the sides. In the quatern measure, you can go back to degrees either approximately, if you use these charts here in the paper, which I will link to. There's ways to do it approximately correctly, right? I mean, very roughly, 1 quatern is the same as 45 degrees. 1 quatern is the same thing as pi over 4 radians, which is the same thing as 45 degrees. And so because of that fact, you can convert roughly back and forth between them. Now, if you want to convert exactly, you do need technology with transcendental functions, which I do those calculations on the sites that I will supply. However, I just want to emphasize something about this. So the thing that I would like to emphasize is that let's suppose a programmer was to use quaterns to render everything. Like, let's suppose you're doing 3D graphics and you're doing the programming for that, and you need to come up with algorithms to do all of the rotations and representation of everything. My point is that all of that could be done totally without ever starting from degrees or ever going back to degrees or radians. So all of these calculations could be done in programming totally algebraically, where the only truncation, you're not truncating an infinite sum. All you're doing at the end is you got an exact value and you're just going to round it to whatever degree of accuracy you want. And so I just wanted to emphasize that. And once again, I will, in the comments to this video, I will link to the paper, and I will also link to all of these online calculators so that you can sort of demonstrate this for yourself. So all of the trigonometric functions and the inverse trigonometric functions, they are all algebraic, and they all work perfectly well, and you can do all of the same types of calculations like cross product, dot product, rotations of vectors in 3D space. All of that kind of stuff can be done with quatern equivalents, so that all of this would be algebraic. So thank you very much for watching the Torus Report tonight, and we will see you again next week. Bye-bye for now.